Reality itself unravels at the edge of a black hole. These cosmic enigmas are not just empty voids, but the universe's ultimate mysteries, where the laws of physics, as we know them, cease to exist. We are about to explore 30 incredible facts that will fundamentally shift your perspective on reality, space, and time. You will discover how time can stretch like taffy and why information might be lost forever. What single idea about the cosmos most captivates your imagination? The very name black hole is a cosmic misdirection. It is not an empty pit in space, but rather the opposite, an object of almost unimaginable density. Picture a star 10 times more massive than our own sun, and then imagine all that material compressed down into a sphere the size of a city. This is the heart of a black hole, a region of spacetime where gravity has won its ultimate victory. The pull is so ferociously strong that the escape velocity, the speed needed to break free, exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing that crosses the boundary can ever return. This boundary is the event horizon, the definitive point of no return. At the very center lies the singularity, a point where all that immense mass is crushed into a volume of zero size, a place where the laws of physics as we understand them simply break down. So when you think of a black hole, do not picture a dark, empty hole. Picture instead an invisible cosmic predator, a place where matter has been pressed into its most extreme and final form. This ultimate collapse begins with a star's final act of defiance. Most black holes are born from the dramatic deaths of stars far more massive than our own sun. Our sun is a stable, middle-aged star fusing hydrogen into helium in its core. It will live out its life for billions of years, eventually becoming a white dwarf, a dense Earth-sized ember. But for a star born with at least 8 times the sun's mass, the story ends with far more violence. Such a star lives fast and dies young, burning through its nuclear fuel in a cosmic blaze lasting only millions of years. When it finally exhausts the elements it can fuse, the outward push of radiation that has supported it for its entire life suddenly vanishes. With nothing left to fight the star's own immense gravity, the core collapses in less than a second. This triggers a cataclysmic rebound explosion known as a supernova, an event so brilliant it can outshine an entire galaxy. What remains after this stellar detonation is the star's compressed heart, its core. If this leftover core contains more than about 3 times the mass of our entire sun, no known force in the universe can stop its final descent. Gravity becomes an unstoppable victor, crushing the core past the point of a neutron star and into oblivion until it wraps spacetime so tightly that not even light can escape. The invisible predator is born. This stellar corpse possesses a gravitational grip so absolute it warps space and time in ways that defy human intuition. If you were to fall feet first toward a typical black hole, your experience would be gruesomely unique. The force of gravity is not uniform. It pulls more strongly on your feet than on your head because your feet are closer to the black hole's center. The difference in this pull, the tidal force, would be overwhelming. You would be stretched lengthwise, pulled taller and thinner, while simultaneously being compressed from the sides. Scientists call this process spaghettification, a playful name for a terrifying end. Your entire body would be transformed into a long, thin stream of atoms, a single line of particles spiraling into the abyss. Yet the size of the black hole dramatically changes your final moments. Falling into a relatively small stellar mass black hole, you would be turned into cosmic spaghetti long before you ever reached the event horizon. A supermassive black hole, however, is a different beast entirely. With its gravity spread over a vast area, the tidal forces at its event horizon are far more gentle. You could theoretically cross the point of no return completely unharmed, at least for a little while. The true horror would begin only after you were already inside, where the now irresistible pull would begin its inexorable work, stretching you toward the waiting singularity. What other cosmic phenomena hide such starkly different fates behind their simple names? The spaghettification of an object reveals the extreme warping of space, but gravity's influence is far more profound. It also warps time itself. This is not science fiction, it is a cornerstone of Einstein's theory of general relativity. Think of the fabric of the universe as a vast, flexible rubber sheet. A massive object like a star or a black hole creates a deep depression in this sheet. This curvature is what we experience as gravity, and it affects everything, including the flow of time. The deeper the gravity well, the more time itself is stretched and slowed. Near a black hole where gravity is at its most intense, this time dilation becomes extreme. For an observer watching from a safe distance, a clock falling toward the event horizon would appear to tick slower and slower, eventually grinding to a near halt just at the boundary. From the perspective of someone bravely orbiting the black hole, however, their own clock would feel perfectly normal. Their hour would pass just like any other hour. But upon returning to Earth, they would face a staggering reality. While 1 hour passed for them, decades, centuries, or even millennia could have flown by for everyone they once knew. This is not a mere illusion, it is a fundamental property of our universe, a direct result of gravity's grip on the very fabric of reality. Our everyday perception of time as a steady, universal river is an illusion that shatters in the face of such cosmic forces. This warping of time and space is not some distant theoretical effect. It is happening right here in our own cosmic neighborhood. At the very heart of our Milky Way galaxy, a silent leviathan resides, a supermassive black hole known as Sagittarius A star. This colossal entity contains a mass equivalent to more than 4 million suns, all compressed into a region of space smaller than our solar system. For decades, its existence was a compelling hypothesis, but proving it required watching the sky with incredible patience and precision. Astronomers focused their most powerful telescopes on the galactic center, tracking the motions of individual stars as they danced through the crowded core. They observed one star in particular, called S2, complete a frantic, looping orbit. This star swings so close to the invisible center that it reaches speeds of thousands of kilometers per second, only to whip back out again on a 16-year journey. The path of these stars, traced over years of observation, revealed an undeniable truth. They were orbiting an invisible, immensely massive object, an object with such a powerful gravitational pull that it could only be one thing: a supermassive black hole. This discovery confirmed that a gravitational monster sits at the center of our own galaxy, fundamentally shaping our cosmic home. Sagittarius A star is not a unique anomaly. Most, if not all, large galaxies are now believed to harbor their own supermassive black holes at their cores. These central black holes are not merely passive residents, they are active architects of their galactic domain. Their immense gravity helps to bind the entire galaxy together, dictating the motion of billions of stars. During their active phases, when they voraciously consume surrounding gas and dust, they can unleash titanic amounts of energy, heating the galactic material and regulating the birth of new stars. The presence of this dark heart makes our galaxy not a static collection of stars, but a dynamic, evolving system, a cosmic dance choreographed by an invisible partner. The silent leviathans at the center of galaxies seem eternal, but even they are not completely immune to the strange laws of quantum physics. A black hole's reign of absolute gravity is challenged at the very edge of its domain. Stephen Hawking proposed a revolutionary idea that turned our understanding on its head. He suggested that black holes can, in fact, evaporate over unimaginable eons. The key lies in the chaotic, frothing nature of empty space itself, where particle and antiparticle pairs constantly blink in and out of existence. Normally, these pairs annihilate each other almost instantly. But if this quantum fluctuation happens right at the precipice of an event horizon, a bizarre theft can occur. One particle falls into the abyss while its partner escapes into the universe. From the perspective of a distant observer, the black hole has just emitted a particle. To balance the cosmic books, the black hole must pay for this emission with a tiny, almost imperceptible amount of its own mass. This slow, steady leak is what we call Hawking radiation. For a typical stellar black hole, this process is agonizingly slow. It would take longer than the current age of the universe, a number so vast it defies comprehension, for it to lose even a fraction of its substance. Yet, given enough time, this quantum whisper would become a roar. As the black hole shrinks, the rate of evaporation accelerates. In its final, fleeting moments, a black hole that has lived for trillions upon trillions of years could potentially vanish in a spectacular flash of energy, a final testament to its existence. This reveals a profound truth that even the most permanent-looking structures in the cosmos are subject to the relentless and patient tick of quantum time. A black hole's terrifying reputation often paints it as a cosmic vacuum cleaner, actively sucking in everything around it. This is perhaps the most persistent and dramatic misunderstanding about them. In reality, a black hole obeys the same gravitational rules as any other object in the universe. Its gravity is simply a result of its mass. To understand this, picture a startling scenario. If our sun were instantly swapped for a black hole of the exact same mass, a moment of profound darkness would fall upon Earth, but our planet's path through space would not change at all. We would continue to orbit this new, invisible center of our solar system in the exact same way, year after year. The immense gravitational anchor holding us in place would remain because the mass has not changed. The danger of a black hole is not in some magical, long-range sucking power. The danger is in its unprecedented density. The sun's mass is spread over a vast sphere nearly 1.4 million kilometers wide. A black hole of the same mass concentrates all that gravitational pull into a point smaller than a city. You would only be in peril if you ventured closer than the sun's original surface, entering a region where the escape velocity soars beyond light speed. From a distance, a black hole's gravity behaves just like that of a star. They are not roaming predators hunting for matter, but rather they are silent traps waiting for something to wander too close. Their absolute darkness makes them invisible, yet we can find them by the cosmic wreckage they leave behind. Astronomers have become masters of indirect detection, piecing together the presence of a black hole by observing how it violently interacts with its environment. One of the most dramatic signatures is the accretion disk, a swirling vortex of gas and dust spiraling inward at near light speed. As this material is pulled toward the event horizon, it is compressed and heated to millions of degrees, becoming a maelstrom of superheated plasma that glows with intense X-ray radiation. It is this brilliant, high-energy scream, detectable by space telescopes, that often betrays the location of an otherwise hidden predator. Another method relies on gravity's ability to bend the very path of light itself. When a black hole passes in front of a more distant star, its immense gravity acts like a lens, warping space and magnifying the star's light, causing it to briefly brighten in a telltale way. But the most stunning evidence arrived just a few years ago, a monumental achievement that felt like science fiction made real. The Event Horizon Telescope collaboration linked observatories across the globe to create a virtual telescope the size of Earth itself. Their target was the supermassive black hole at the heart of the galaxy Messier 87, a beast with the mass of 6.5 billion suns. The image they produced was not of the black hole itself, for that is impossible, but of its dark shadow, a perfect circle of blackness silhouetted against the fiery glow of its accretion disk. This iconic image confirmed the existence of these cosmic giants in the most direct way imaginable, allowing us to essentially see the edge of reality. These cosmic predators are not a single, uniform class. They come in a staggering range of sizes, from the relatively small to the almost incomprehensibly vast. The most common type is the stellar mass black hole. These are the remnants of those massive stellar collapses we discussed, typically ranging from about 3 to 100 times the mass of our Sun. Scattered throughout galaxies, they are the silent graves of dead stars. Then we have the giants, the supermassive black holes. These are the monsters that lurk in galactic centers, boasting masses from millions to billions of solar masses. Sagittarius, a star at our Milky Way's heart, is a prime example of this colossal class. But what about the space between these two extremes? For a long time, a crucial category seemed to be missing, a middle child that astronomers struggled to find. These are the intermediate mass black holes, theorized to exist with masses between 100 and 100,000 suns. Evidence for them has been elusive, but hints have emerged in the hearts of some globular clusters and in the peculiar, faint glow of certain ultra-luminous X-ray sources. Their very existence is a key puzzle piece, as they could be the building blocks, the seeds from which supermassive black holes grew in the early universe. How exactly these supermassive giants formed so quickly after the Big Bang remains one of the great open questions in cosmology. Did they grow from the collapse of enormous primordial gas clouds, or did they start as smaller black holes that voraciously merged and consumed their way to unimaginable sizes? The hunt for the elusive intermediate black hole is crucial to solving this cosmic mystery. The stillness of a black hole is a profound illusion. While they appear as perfect spheres of darkness, many are actually cosmic whirlpools spinning at a significant fraction of the speed of light. This rotation fundamentally changes their structure and creates even more bizarre regions of warped spacetime. The simplest theoretical model is the Schwarzschild black hole, a perfectly static and non-rotating object. But this is a cosmic ideal, a fiction that rarely exists in nature. The reality is far more dynamic. Most stars rotate, and as a massive star collapses into a black hole, this spin is conserved and amplified, just like an ice skater pulling in their arms to spin faster. The result is a Kerr black hole, a rapidly rotating dynamo of pure gravity. This spin stretches the event horizon from a perfect sphere into a flattened spheroid and creates a new, even more incredible boundary just outside it called the ergosphere. The ergosphere is a region where the black hole's rotation is so powerful it draggles the very fabric of spacetime along with it. Imagine spacetime as a flowing river. Within the ergosphere, the current is so strong that nothing can stand still, not even light. Every object is forced to move in the direction of the black hole's spin. This leads to a truly astounding theoretical possibility: the extraction of energy from the black hole itself through what is known as the Penrose process. A daring civilization could, in theory, fire a projectile into the ergosphere, allowing it to split in two. One part falls into the event horizon, while the other escapes with more energy than the original projectile possessed. The energy gained comes directly from the black hole's rotational momentum, slowing its spin by a minuscule amount. This is not magic, it is pure physics, a testament to how these objects are not just simple traps but complex engines capable of storing and releasing phenomenal power. This relentless spin and warping of space, however, is merely a prelude to the true unknown. Deeper than the event horizon, beyond the whirling ergosphere, lies the ultimate cosmic mystery, the singularity. This is the point at the very center where the collapsed star's entire mass is crushed into a volume of zero size. According to the equations of general relativity, this results in infinite density and infinite curvature of spacetime. The word infinity is not just a mathematical convenience here. It is a screaming alarm that our understanding of the universe has hit a wall. At the singularity, the reliable laws of physics that govern everything from falling apples to orbiting planets simply break down and cease to have any meaning. Cause and effect, the very fabric of reality as we perceive it, unravels completely. This is not just a place we cannot see, it is a place we cannot describe with our current knowledge. The problem is a fundamental clash of titans. General relativity, which masterfully describes the large-scale force of gravity and the warping of spacetime, is utterly incompatible with quantum mechanics, the set of rules that governs the bizarre behavior of the very small. The singularity is a realm where the immense gravity of the cosmos is focused on a single, infinitesimal point, a domain where both sets of laws must somehow unite. To truly know what happens at the heart of a black hole, we require a theory of quantum gravity, a single framework that can marry the world of the very large with the world of the very small. This holy grail of physics, sought after by the greatest scientific minds, remains elusive. The singularity, therefore, is more than a cosmic object. It is the final frontier of human knowledge, a stark reminder of the limits of our current vision and the breathtaking mysteries that still await a solution. The violent birth of a black hole can tear a hole in the cosmos itself. When a truly massive star reaches the end of its life and its core collapses, not all of the surrounding material falls into the newborn abyss. Some of it is funneled by powerful magnetic fields into twin jets, narrow beams of matter and radiation that scream outward from the star's poles at over 99.9% the speed of light. These jets are the particle accelerators of the gods, and if one of them is pointed directly at Earth, we witness the single most powerful explosion in the universe since the Big Bang. We call this event a gamma-ray burst. For a few fleeting seconds, this single event can release more energy than our Sun will emit over its entire 10 billion-year lifetime, outshining every star in its galaxy combined. The flash is so intensely bright that our satellites can detect it from the very edge of the observable universe. From galaxies so far away, their light has been traveling to us for over 13 billion years. You are essentially watching a cosmic beacon that signaled the death of a star and the violent creation of a black hole when our universe was in its infancy. It is a direct message from the past, a testament to a fury so absolute it defies all human scale. This warping of spacetime around a black hole does more than just slow time. It actively bends the very path that light travels. This phenomenon, called gravitational lensing, turns the cosmos into a funhouse of mirrors. Picture a perfectly taut, stretchy rubber sheet representing the fabric of space. Placing a heavy bowling ball in the center creates a deep dip. Now, if you roll a tiny marble past the bowling ball, its straight path will curve inward following the contour of the dip. A black hole creates an unimaginably deep dip in spacetime, and light, which always follows the shortest path through this curved geometry, has no choice but to bend along with it. This means the light from a distant star, which would normally travel in a straight line to our telescopes, is forced to take a curved detour around the black hole's immense gravity. The result is that the star's apparent position in the sky is shifted, as if seen through a distorted lens, but the effects can become far more dramatic. If the alignment is perfect, with the black hole directly between us and a background galaxy, the light from that galaxy can be bent and smeared into a complete circle of light encircling the black hole's shadow. This perfect halo is known as an Einstein ring, a stunning and rare confirmation of a prediction made over a century ago. More commonly, the alignment is slightly off, creating multiple distorted images of the same galaxy or stretching its light into long, faint arcs. Astronomers use this cosmic trick not just as a way to find hidden black holes, but as a direct test of Einstein's universe. Every distorted image, every Einstein ring, is a message written in bent starlight, telling us that the great physicist was right about the very fabric of our reality. That distorted starlight reveals the warping of space, but it conceals a deeper crisis brewing at the event horizon itself. This crisis is known as the black hole information paradox, and it strikes at the very heart of our understanding of reality. The problem begins with two sets of laws, both incredibly successful, that give us completely contradictory answers. On one hand, quantum mechanics, the rules governing the subatomic world, holds a sacred principle: information cannot be created or destroyed. If you burn a book, the information within it seems lost, but in theory, a being with infinite knowledge could collect every single ash particle, trace every wisp of smoke, and reconstruct the entire book from the chaotic aftermath. The information is merely scrambled, not erased from the universe. On the other hand, general relativity tells us that anything crossing a black hole's event horizon is lost forever to our universe, its information trapped behind an impenetrable curtain. Now add Stephen Hawking's discovery to the mix. Hawking radiation causes a black hole to slowly evaporate over eons until it vanishes completely. So here is the devastating question: what happens to all the information about every atom, every book, every star that ever fell in? If the black hole disappears, does that information vanish with it, violating quantum law? Or does it somehow escape, violating relativity's rule that nothing gets out? This is not a trivial puzzle. It suggests that our most fundamental theories of physics are fundamentally incompatible, and that one of them must be wrong or at least incomplete. Solving this paradox has forced physicists to propose radical ideas. One is the holographic principle, the mind-bending suggestion that all the information about what fell into a three-dimensional black hole is not lost inside, but is instead encoded on a two-dimensional surface at its event horizon, like a cosmic fingerprint. Another, even more extreme idea is the firewall hypothesis, which suggests the event horizon is not a smooth gateway but a raging wall of high-energy particles that would instantly incinerate anything crossing it. These are not just wild guesses, they are desperate attempts to reconcile two pillars of modern science. The information paradox is more than a theoretical debate. It is a battle for the soul of physics, forcing us to ask whether the universe is fundamentally predictable or if some truths are truly and forever lost to the void. This elegant simplicity is captured in the no-hair theorem. The name is a metaphor suggesting that a black hole, like a bald head, has no complicated features. According to this idea, once matter crosses the event horizon, every single detail about it is erased. Was it a star made of hydrogen, a planet rich in iron, or a library of ancient books? The black hole does not care. It swallows everything, and all that remains for an outside observer to measure are three, and only three, fundamental properties: its mass, its electric charge, and its spin. Everything that made the fallen object unique, its composition, its structure, its history, is permanently lost, shaved away into the abyss. This theorem provides a beautifully clean description of these cosmic objects, but its stark finality is precisely what fuels the fire of the information paradox. If the no-hair theorem is correct, then information truly is destroyed, violating a core principle of quantum physics. Yet, the universe rarely favors such absolute simplicity. Recent theoretical work has begun to challenge this clean-shaven view, proposing that black holes might in fact have a kind of soft hair. This is not literal hair, of course, but a term for subtle, complex structures or imprints that could potentially linger at the event horizon. These faint traces might be formed from zero-energy particles or gravitational waves, creating a unique signature based on what fell in. If this soft hair exists, it could act as a sort of cosmic ledger, preserving information about the black hole's diet without violating the rule that nothing escapes from inside. The implications are monumental. It could mean that information is not lost after all, but merely transformed and stored in this exotic, two-dimensional record at the very boundary of reality. This ongoing battle between the elegant no-hair theorem and the messy possibility of soft hair is more than academic. It is a direct assault on our understanding of whether the universe forgets or if it remembers everything forever. The question of what lies at the singularity may be unanswerable, but the nature of black holes themselves is far more diverse than we once believed. not all of these cosmic traps were forged in the death of stars. A more ancient and elusive breed could be hiding in the darkness, relics from the very birth of the cosmos. These are primordial black holes, and if they exist, they are living fossils from the universe's first chaotic moments. Theorists propose that in the incredibly dense and hot soup of the infant universe, just instants after the Big Bang, random fluctuations in density could have been so extreme that pockets of space spontaneously collapsed under their own weight. This would have created black holes not from dying stars, but from the raw energy of creation itself. Their potential sizes are as bizarre as their origin. A primordial black hole could be as small as an asteroid, yet contain the mass of an entire mountain, or as large as a planet, holding the mass of several Earths compressed into a space smaller than a marble. Their staggering density is what makes them such compelling candidates for the universe's greatest mystery, dark matter. We know dark matter exists because of its gravitational pull on galaxies, but we have never directly seen it. These tiny, invisible black holes sprinkled throughout the cosmos could be the hidden mass that binds galaxies together. The hunt for them is a frontier of modern astronomy. Scientists search for the telltale flash of light when one passes in front of a distant star, its gravity briefly focusing the starlight like a lens. They also listen for the faint, high-frequency ripples in spacetime they might create. Perhaps the most thrilling possibility is that one of these ancient wanderers, a miniature black hole forged in the first second of time, could be drifting silently through our own solar system right now, a ghost from the dawn of everything passing unseen in the vast dark between the planets. The silent drift of primordial black holes is a cosmic whisper compared to the thunderous collisions that reshape the fabric of reality. For decades, Einstein predicted that the universe should be filled with gravitational waves, ripples in spacetime caused by the most violent events imaginable. But these ripples are incredibly faint, and for 100 years they remained undetected, a ghostly echo of a theory waiting for proof. That proof arrived on September 14, 2015, when the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, registered a signal that would change astronomy forever. The signal was a rising chirp, a cosmic song that lasted for less than half a second. It began with a low-frequency murmur as two massive black holes, each about 30 times the mass of our Sun, began their final, fatal dance. They spiraled around each other hundreds of times per second, moving closer and faster in a tightening orbit that warped the space around them, sending out powerful waves. In the last few milliseconds, the two black holes slammed together, merging into a single, more massive object. In that cataclysmic instant, a phenomenal amount of energy, equivalent to 3 times the mass of our Sun, was converted directly into ripples of spacetime and radiated outward across the universe. The new, larger black hole rang like a bell, vibrating and settling into its new form, its final gravitational waves fading into silence. This event happened 1.3 billion years ago, and its faint ripple finally reached Earth, stretching and squeezing the very space inside the LIGO detectors by a distance 1,000 times smaller than the nucleus of an atom. This impossibly tiny wiggle was our first direct confirmation that black holes can merge, and that spacetime itself can be made to ripple. We had learned to listen to the universe, to hear the invisible collisions of the darkest objects in the cosmos. That final, silent merger of black holes is a dance of pure gravity in the dark. But when a black hole feasts on more than just another of its kind, the result is a cosmic fireworks display of unimaginable brilliance. The violence begins long before any material reaches the point of no return. A star or a cloud of gas that wanders too close is caught in an irresistible gravitational grip. The black hole's tidal forces, the difference in pull between the near and far sides of the object, stretch it relentlessly. A star is pulled apart into a long, thin stream of superheated gas, a process literally called a tidal disruption event. This stream of stellar debris does not fall straight in. Instead, it wraps around the black hole, colliding with itself in a chaotic storm. The individual particles transfer energy to one another, cancelling out their sideways motions and settling into a vast, flattened, rotating whirlpool, the accretion disk. This disk is a maelstrom of doomed matter, a cosmic hurricane spinning at nearly the speed of light. The material on the inner edge of the disk races furiously, while the outer lanes move more slowly, creating immense friction as these layers grind against each other. This friction, combined with the crushing pressure of the black hole's gravity, heats the gas to temperatures of millions of degrees. The disk is no longer just hot gas, it becomes a swirling ocean of incandescent plasma, glowing with a ferocious intensity. It is this process that transforms the invisible into the visible. The superheated plasma emits a torrent of radiation across the entire electromagnetic spectrum, from radio waves to visible light to the most energetic photons of all, X-rays. It is this high-energy scream, this brilliant X-ray beacon, that cuts through the darkness of space and lands in the sensors of our orbiting telescopes. For astronomers, this intense light show is a dinner bell. The glow of an accretion disk is often the very first clue that a hidden black hole is active, a luminous signpost pointing toward a gravitational monster and allowing us to study its properties from the safety of millions of light years away. These brilliant beacons of plasma are a black hole's most violent outburst. While an accretion disk represents matter spiraling inward, relativistic jets are the exact opposite, colossal geysers of energy and particles blasted outward at nearly the speed of light. These are not made from material that is falling in, they are a direct theft of the black hole's own power. The engine for this cosmic fireworks display is the black hole's furious spin and its immensely powerful magnetic fields. As the black hole rotates, it drags the magnetic fields embedded in its accretion disk into a tightly wound, tornado-like structure. This creates a powerful dynamo, channeling some of the infalling material and accelerating it along the black hole's polar axis, the only paths of least resistance. The particles caught in this magnetic slingshot are hurled across space in two narrow, oppositely directed beams. The images are staggering, the jet erupting from the supermassive black hole in galaxy M87 stretches for thousands of light years, a searchlight beam of energy longer than our entire Milky Way galaxy. These jets are not gentle streams, they are tsunamis of plasma traveling so fast that time dilation warps our view of them. To us, they appear to move faster than light, a relativistic illusion born of their incredible velocity. Their impact on the surrounding cosmos is profound. When these jets slam into the tenuous gas that lingers between galaxies, they inject immense energy, heating the material and preventing it from cooling and collapsing to form new stars. In this way, a single black hole can act as a cosmic thermostat, regulating the growth of its entire galaxy and shaping the large-scale structure of the universe itself. It is a paradoxical truth. The same object that devours light and matter can also be the source of the most powerful fountains of energy we have ever observed. This holographic principle, born from the paradoxes of black holes, leads to one of the most radical ideas in all of science. What if our universe, with its rich three-dimensional depth, its soaring galaxies and swirling nebulae, is not the fundamental reality? What if it is a magnificent illusion, a holographic projection from a two-dimensional surface? This is not science fiction, but a serious theoretical proposal to solve the black hole information paradox. The mathematics suggests that all the information needed to describe everything within a volume of space, every star, every planet, every one of us, could be entirely encoded on the lower dimensional boundary of that space. For a black hole, this boundary is its event horizon. The information about every atom that ever fell in is not lost inside the singularity, but is painted like a cosmic tattoo onto the surface of the horizon. Our universe, in the most extreme version of this idea, could be behaving in a similar way. the three-dimensional reality we experience with all its sights and sounds could be a projection from a vast, distant, two-dimensional surface that surrounds us at the edge of the observable cosmos. Think of it like watching a high-definition movie on a flat screen. The image has depth and movement, a three-dimensional world you feel you could step into, but every bit of that information is stored on the two-dimensional surface of the screen. In this grand cosmic analogy, we are not the audience, we are the characters in the movie, living inside the projection, completely unaware that our entire reality might be a shadow play cast from the edges of space itself. This means that the fundamental building blocks of reality may not be particles or strings vibrating in three dimensions, but rather bits of information, ones and zeros, written on the ultimate celestial sphere. The solidity of the world around you, the feeling of your feet on the ground, the vast, empty space between stars, all of it could be an emergent property, a consequence of this immense cosmic code. It is an idea that fundamentally demotes our experience of the universe, suggesting that depth itself is a beautiful and convincing illusion. The holographic universe is a profound illusion, but what if that illusion could be punctured, creating a shortcut through the cosmos itself? The equations of general relativity, which so accurately describe black holes, also contain a tantalizing possibility: wormholes. Often called Einstein-Rosen bridges, these are not mere science fiction. They are hypothetical tunnels through the folded fabric of spacetime. The mathematics suggests that the intense gravitational field of a black hole could, in theory, connect to its exact opposite, a white hole. While a black hole is a one-way street where nothing can escape, a white hole would be a place where nothing can enter, a cosmic fountain eternally spewing matter and energy out into the universe. A wormhole would be the bridge between these 2 points, a celestial subway tunnel linking 2 distant regions of space, or perhaps even 2 different moments in time. The entrance to this tunnel would look very much like a black hole, a gravitational pit from which there seems no return. But instead of ending in a crushing singularity, the journey would continue through the throat of the wormhole, emerging from the white hole in a completely different corner of the cosmos or in a different era entirely. The sheer potential is staggering, a way to traverse distances of millions of light years in a single step, making interstellar travel not just a dream but a theoretical possibility. Yet this incredible promise comes with equally immense and sobering problems. The first and most critical is stability. The kind of wormhole predicted by Einstein's equations would be incredibly fragile, pinching shut into a singularity in an instant, long before even a single particle of light could make the trip. The tunnel would collapse faster than it could be traversed. To keep it open, you would need a form of matter with negative energy density, something that exerts a kind of anti-gravity, propping the throat of the wormhole open against its own immense gravitational pull. While quantum mechanics allows for tiny amounts of negative energy in specific circumstances, we have no idea how to create or sustain the vast quantities needed for a traversable wormhole. And even if you solved that, you would still face the same deadly tidal forces present in any black hole, the spaghettification that would stretch any traveler into a stream of atoms. So while the mathematics offers a breathtaking glimpse of a connected universe, a cosmic network of shortcuts, the physical barriers seem almost insurmountable. They remain a thrilling testament to the strange and hidden architecture of spacetime, a reminder that the universe may be far more interconnected than it appears, even if those connections are forever locked away behind the veil of physical law. The silent giant at a galaxy's core is far more than a passive occupant. It acts as a master regulator, its violent outburst shaping the very evolution of its cosmic home. This is a story of feedback, a delicate and powerful symbiosis between the black hole and the billions of stars surrounding it. When the black hole actively feeds, the resulting accretion disk and relativistic jets flood the galaxy with immense energy. This energy heats the vast reservoirs of cool gas scattered between the stars, the very raw material needed to form new suns. Think of it as a cosmic thermostat. If the gas remains too hot, it cannot collapse under its own gravity to ignite new stellar nurseries. The black hole's furious activity essentially puts the brakes on star formation, preventing the galaxy from growing too large too fast. This process creates an observed balance so precise it seems almost designed. Astronomers have found a remarkable correlation. The mass of a galaxy's central supermassive black hole is directly proportional to the mass and properties of the galaxy's central bulge, the dense swarm of stars at its heart. A larger black hole always seems to reside in a galaxy with a larger bulge. This connection is too strong to be a coincidence. It tells us that the black hole and its galaxy did not evolve independently. They grew up together, influencing each other across billions of years. The galaxy feeds the black hole with occasional meals of gas and stars, and in return, the black hole governs the galaxy's growth, its energetic feedback ensuring a controlled and stable evolution. This cosmic dance reveals a profound truth, that the largest structures in the universe are intimately connected to the most destructive forces within them. The drama of a galactic core is written in the death of stars. When one ventures too close to a supermassive black hole, it experiences a gravitational pull so extreme that the star's own self-gravity cannot hold it together. The difference in the black hole's tug between the star's near side and its far side overwhelms every atomic bond. The star is not simply crushed, it is stretched, elongated into a long, thin stream of gas in a process known as a tidal disruption event. It is the ultimate cosmic unraveling. This stellar spaghetti then wraps around the black hole in a chaotic whirl, but the star's material does not all vanish into the void. In a spectacular release of energy, roughly half of the stellar debris is violently flung away into the depths of space, ejected at incredible speeds. The remaining half, however, is ensnared. It settles into a furious, temporary accretion disk swirling at near light speed. The friction and compression within this disk of doomed star stuff heat it to millions of degrees, causing it to shine with a brilliant flare across the electromagnetic spectrum. For a few brief months, this event can outshine every star in its host galaxy combined. For astronomers, this transient blaze is a precious gift. It acts like a cosmic flashbulb, momentarily illuminating a previously dark and dormant monster. By studying the light curve and the radiation from this flare, scientists can measure the mass of the hidden black hole, understand its feeding habits, and probe the very physics of accretion in the most extreme environment imaginable. A single star's destruction becomes a powerful tool to unveil the secrets of the invisible giant that destroyed it. The bizarre leak of Hawking radiation means that black holes are not truly black and they are not truly cold. They possess a temperature, a direct link to the quantum chaos at their event horizons. This temperature, however, is not what you would feel on a warm day. It is a measure of the energy of the Hawking radiation they emit, and it holds a strange and counterintuitive secret. The temperature of a black hole is inversely proportional to its mass. The more massive a black hole is, the colder it becomes. A small, stellar mass black hole would be relatively hot, while a supermassive giant like Sagittarius A star would be profoundly frigid. This relationship turns our everyday experience on its head. A dying ember is hot while a massive bonfire is cool. For a typical stellar black hole, this theoretical temperature is only a fraction of a degree above absolute zero, far colder than the deepest reaches of interstellar space. And this is the key to their current fate. Our universe is filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation, which has a temperature of about 2.7 degrees above absolute zero. For all known black holes, their Hawking radiation temperature is lower than this universal background warmth. This means they are currently absorbing more energy from the cosmos than they are emitting through Hawking radiation. They are growing, not shrinking, gaining mass from the faint whisper of ancient light that fills all of space. Only in the distant, distant future, when the expansion of the universe has stretched the cosmic background radiation to a temperature even lower than their own, will black holes finally begin to lose mass faster than they gain it, starting their slow, final journey toward evaporation. That first historic image of a black hole was not the object itself, but its ghost, a shadow cast against the fire. The glowing orange ring we all saw is the light from the superheated accretion disk, but that light is not traveling in a straight line. The black hole's immense gravity acts like a celestial lens, warping the paths of the photons orbiting just outside the point of no return. This creates a bizarre optical effect, a ring of light that is actually composed of photons that have looped around the black hole multiple times before escaping to reach our telescopes. At the very center of this brilliant ring lies the true mystery, the dark shadow. This is not the event horizon. The event horizon itself is far smaller and is fundamentally invisible, a boundary from which no light can ever escape. The shadow we see is a much larger region of darkness, a consequence of light paths being bent so severely that they spiral inward, forever trapped. The size of this dark void was precisely predicted by Einstein's equations, a perfect circle of nothingness approximately 2.5 times wider than the actual event horizon. Seeing that shadow was like seeing a silhouette, confirming the shape and size of an invisible object by the void it carves out of the light. It was a direct visual proof that we were looking at a region of space where gravity had twisted the paths of light into a perfect prison. What other invisible giants might we map by the darkness they cast upon the cosmos? Our understanding of physics rests upon a comforting cosmic rule that the universe protects us from its own deepest flaws. This principle is known as the cosmic censorship hypothesis. It proposes a fundamental safeguard that every singularity, that point of infinite density where physics breaks down, must be permanently hidden from our view, forever cloaked behind the impenetrable curtain of an event horizon. It is as if the universe has drawn a discreet veil over its own impossible core, ensuring that the predictable laws governing our reality remain intact everywhere outside. But what if that veil could be torn away? This terrifying and thrilling possibility is the naked singularity. Imagine a point of infinite density where gravity becomes truly infinite and the fabric of causality is shredded, but with no event horizon to shield the outside universe from its chaotic influence. Such an object would be a wound in the fabric of reality, a place where the universe's rulebook is burned in plain sight. The gravitational forces around a naked singularity would be so bizarre and unpredictable that they could theoretically warp time into closed loops, creating potential for time travel and violating our most fundamental understanding of cause and effect. The very possibility forces physicists to confront a profound question: is the orderly cosmos we observe a fundamental truth, or merely a local ordinance, a calm neighborhood in a universe that is, deep down, lawless and wild? While no definitive naked singularity has ever been observed, and most scientists believe nature abhors such an object, the mere theoretical possibility continues to drive research at the very edge of our knowledge, a ghost in the equations that reminds us how little we truly understand. The orderly veil of cosmic censorship hides a seething chaos at the very edge of reality. The event horizon is not a calm, definitive line, but a stormy frontier where the rules of the very small violently clash with the rules of the very large. Here, in the grip of unimaginable gravity, the quantum nature of the universe becomes undeniable. Empty space is not truly empty. It is a bubbling, frothing sea of potential, where pairs of virtual particles and antiparticles constantly wink into existence, borrowing energy from the vacuum for an impossibly brief moment before they collide and annihilate, paying the energy back. This quantum jitter is happening everywhere all the time, even in the room around you. But at the precipice of a black hole, this delicate dance is catastrophically interrupted. If a particle pair emerges right at the event horizon, one particle can fall across the boundary while its partner is left stranded outside. The abandoned particle, suddenly real and unable to annihilate with its partner, flies off into space. From our perspective, the black hole has just emitted a particle. This is the true mechanism of Hawking radiation. But to maintain the balance of energy, the particle that fell inward must have negative energy relative to the outside universe. This sounds bizarre, but in the warped geometry near the horizon, it is possible. When the black hole absorbs this negative energy, it effectively loses a tiny amount of mass. This process is an excruciatingly slow drip for a large black hole, but it is a continuous one. Every single emission of a Hawking particle is a direct transaction between the quantum world and the gravitational world, a microscopic theft of mass from the black hole itself. This is why Hawking's discovery was so revolutionary. It was the first solid theoretical bridge connecting Einstein's general relativity, the theory of gravity, with quantum mechanics, the theory of the small. It suggests that gravity, the force that shapes the cosmos, must ultimately have a quantum explanation of its own. The silent, dark giant is slowly, patiently, being dismantled by the faint, persistent whisper of nothingness itself. That faint quantum whisper is a slow leak, but a rotating black hole conceals a far more potent power source. Its spin contains a staggering reservoir of energy, a cosmic battery waiting to be tapped by any civilization with the audacity and knowledge to try. The key lies in the ergosphere, that whirling region of space just outside the event horizon where the black hole's rotation drags spacetime itself along for the ride. This cosmic carousel creates a unique opportunity, a theoretical energy extraction method known as the Penrose process. Imagine a daring mission where a spacecraft ventures into the ergosphere and releases a payload. The craft itself must fire its thrusters to escape, but the payload splits in two. One fragment, carrying negative energy, is deliberately steered to fall across the event horizon. The laws of physics demand that to conserve energy, the other fragment is flung back out into space, but now it carries more energy than the entire original object possessed. Where did this extra energy come from? It was stolen directly from the black hole's rotational momentum. The infalling fragment, with its negative energy, effectively slows the black hole's spin by a minuscule amount, and that lost rotational energy is transferred to the escaping fragment. It is a perfect cosmic robbery, turning the most destructive object in the universe into a dynamo. This mechanical process, however, might be nature's own preferred method on a grander scale. Many of the most powerful black holes in the universe are surrounded by intensely magnetized accretion disks. As the black hole spins, it twists these magnetic field lines into a tightly wound, colossal structure. This creates a powerful circuit, a natural battery with the black hole itself as the rotor. Charged particles from the accretion disk get caught in these magnetic fields and are accelerated along the black hole's polar axis, screaming away at nearly the speed of light. This is the Blandford-Zajic process, and it is the leading theoretical explanation for the mind-boggling power of relativistic jets. The energy for those jets, which can outshine entire galaxies, does not come from nuclear fusion or any chemical process. It is gravitational and rotational energy, extracted directly from the black hole's spin by the cosmic dynamo of its own magnetic fields. This means the most luminous objects we see in the universe are powered not by something burning, but by the raw, twisted spacetime around a black hole. These cosmic engines challenge our very definition of power, proving that gravity itself, when harnessed by a spinning singularity, can become the ultimate fuel for creation on an unimaginable scale. Our galactic center holds a sleeping giant, while other supermassive black holes blaze as brilliant quasars, actively devouring stars and gas. Sagittarius A is remarkably quiet. It is not a dormant volcano, but one that only occasionally rumbles. It feeds on small clouds of gas and the rare, unlucky star, yet it does not sustain the vast, luminous accretion disk that would mark it as a truly active monster. This peaceful state is a gift. An active galactic nucleus with its searing radiation and relativistic jets would sterilize vast regions of the galaxy, making the emergence of complex life like us nearly impossible. So why is our central black hole so calm? The primary reason seems to be a simple lack of sustenance. The region around it is relatively clean, with little free-falling gas to fuel a continuous fire. Galactic dynamics and past feedback cycles may have already cleared out the available fuel, putting the black hole on a lean diet. Our position in a stable galactic suburb, far from the violent core, is a direct result of this cosmic peace. The quiet of Sagittarius A star tells a profound story about our cosmic neighborhood, a tale of a past fury that has settled into a long, deep slumber, allowing for the quiet evolution of stars, planets, and life itself in its peaceful shadow. This final frontier of physics, the silent giant in our galactic core, is far more than a cosmic curiosity. Black holes are the universe's ultimate laboratories, forcing us to confront the deepest questions about reality itself. Every paradox they present, from the missing information to the nature of the singularity, is a direct challenge to our understanding of physics. The relentless pull of gravity described by Einstein's general relativity clashes violently with the fuzzy, probabilistic rules of quantum mechanics. Yet, at the edge of a black hole, these two titanic theories must meet. They have no choice. The quest to understand what happens in that extreme environment, to reconcile the warping of spacetime with the jitter of quantum particles, is the single greatest driving force behind the search for a theory of quantum gravity. This is the hunt for a theory of everything, a single, elegant framework that can describe all the forces of the cosmos, from the immense scale of galaxies down to the tiniest vibrations of strings. Black holes are not just testing grounds, they are the final exam. They are the only places in the universe where conditions are so extreme that our current laws break down, revealing their own limitations. In trying to comprehend these dark abysses, we are not merely learning about cosmic monsters. We are deciphering the fundamental rules that govern everything, from the birth of the universe to the nature of time itself. They are the key that could one day unlock the deepest secrets of existence. These cosmic enigmas have taken us from the death of stars to the edge of reality itself. We have witnessed matter stretched into streams of atoms, seen time slow to a crawl, and heard the echo of black holes colliding across 1 billion years. We have discovered that these are not merely destructive voids but fundamental architects of the cosmos, sculpting galaxies, regulating the birth of stars, and guarding the deepest secrets of physics. They are paradoxes made real, where the predictable universe we know gives way to a realm of infinite density and lost information. This journey through 30 astonishing facts has hopefully done more than just inform you. It has shifted your perspective, revealing a universe far stranger, more dynamic, and more interconnected than we often dare to believe. Black holes are the universe's ultimate teachers, challenging everything we thought we knew about space, time, and existence. The next time you gaze up at the night sky, remember that hidden within that darkness are these incredible engines of creation and destruction, each one a gateway to a deeper understanding. We would love to hear which of these facts reshaped your view of the cosmos the most, so share your mind-blown moment with us in the comments below.